This is Mr. Gillum, and today we're going to start learning about how to solve one-step equations using algebra. And so what you're trying to keep in mind when solving equations algebraically, or equations with letters, is that you are trying to isolate the variable on one side of the equality. All right, and that might be a really confusing statement right now, but basically, because we're just talking about one-step equations today, you will see a variable, and you will see an operation near that variable with a constant. Okay, if you see addition, you'll use its inverse operation, subtraction. Subtraction's inverse is addition. Multiply, you would divide, and obviously division's inverse would be multiplication. And so, because these are just one-step equations, and although you may be able to do these in your head with mental math, they're not always going to be one-step equations. In fact, they're going to get harder and harder until you'll actually be able to do some pretty impressive things with algebra. But even though these are very short equations, I want you to really practice the proper steps and work on the elementary ones, the one-steppers, so that when we get to the 2 and 3 and 4-step equations, you have that solid foundation. All right, so please make sure to write down everything, every little bit of work that I write down, because this is how we're going to do our multi-step equations as well, and it'll help you to be organized. All right, and I referenced earlier, I think, that what we had done with solving equations so far is we thought of it as a balance. And on the balance, the equal sign was right in the middle, and we wanted to make sure that both sides stayed balanced. And so on our balances, if we saw that we needed to take away from one side, we also had to take the same amount away from the other side. And that goes for all operations. So anytime you manipulate one side of the equation, you have to do the same action to the other. There's actually properties for each of these, and they're called properties of equality. And so in this case, with mental math, I would know there is a number here for m that I could add 4 to for it to equal 6. Now most of us probably can know that m must equal 2. However, even though you can do it with mental math, I would like you to start showing the appropriate steps for what we're going to end up doing is multi-step equations. And so in preparation for that, we're going to actually show algebraically why m must equal 2 by using inverse operations. And so I have a value here, and I'm adding 4, and it equals 6. The first thing I'm going to do is I'm going to almost similarly to a balance, is I'm going to draw a line right through the equal sign, and that's going to be either side of my equation. Okay, that equal sign is going to separate each side of the balance. And I know that on the balance, if I had 1 unknown over here and 3 over here, that my unknown was worth 3. And so that's the same strategy we're going to use when solving our one-step equations. We would like the variable to be the only thing left on one side of the balance, and whatever is left on the other side of the balance, we will know that is what it's equal to. So in this case, I have the variable m, and I have a constant of positive 4, or plus 4. I would like to use inverse operations to isolate the variable. So in this case, because it's adding 4, I'm going to subtract 4 from both sides of the equation. And so when I do that, sometimes students get confused because they think I'm just subtracting the 4 from this 4 and just subtracting the 4 from the 6. But really, a better way to think of this, and it's kind of tricky, would be to, even though I'm writing minus 4 and minus 4, I would like you to think of it as m plus 4 minus 4 equals 6 minus 4. So as you can see, I've done the same thing to both sides of the equation by decreasing both sides by 4. And now this is a matter of adding like terms. I have an m, a positive 4, and a negative 4. And so the constants can be combined together to make 0. So m plus 0 equals 2. Or, well, anything, 0 just means nothing. M plus nothing else is still m, so m must equal 2. So, although it looks like a lot of steps for this one-step equation, and you could probably do this problem with mental math, for the multi-step equations, this is going to be very tricky. So we're going to practice the right way right now. In this case, in the second equation here, I'm going to go ahead and mark where my equal sign is, so I know if I do an operation on one side of that line, I have to do the same operation on the other. I'm going to use inverse operations. Now I'm trying to isolate or get the x all by itself, the only thing on this side. Unfortunately, we had this minus 7. The inverse of subtraction is addition, so I will add 7 to both sides. We talked about this property a little bit. This is called the inverse property of addition. It tells me that if I add opposites, it equals 0. So in this case, those will add up to 0, and x plus 0 is still x. On the right-hand side of the equation, I have 3 plus 7, which I know is 10. And so then I know x must equal 10. And again, we've practiced solving these equations with the balance in class visually. So this problem is a little trickier. The variable is actually on the right-hand side instead of the left-hand side. Although it doesn't matter as long as the variable is isolated with only the variable on one side of the equation, then I've solved it. So again, in this case, it looks like I have an x minus 6, and the inverse of subtraction is addition. So I will add 6 to both sides. In this case, we have 9 and an equal sign and then x. Now, I know that negative 6 and 6 add up to 0, and x plus 0 is really still x. So that's what all this was right here, first time we did it. But you can think of 9 equals x the same way as x equals 9. All right. It's called the reflexive property. And then finally, if I'm trying to solve for k in the last problem, in this case I have some decimals, but that's alright because it doesn't matter what's over there with k, whatever it is, I need to do the inverse operation. So in this case, what I'm going to do is I'm going to add 4.3 to both sides of the equation, and I did it on the side this way, so we're clear that I'm just adding it to one side. I'm just adding it inside the tray. I'm not just adding it specifically just to this negative 4.3. I'm adding it to the whole side as a whole. But combining like terms tells me that negative 4.3 and 4.3 are opposites, so they'll add up to 0, and k plus 0 is still k. On the left-hand side, 4.3 and 3.4 together make 7.7. So k must equal 7.7. All right, so these are one-step equalities that we're solving, and we're using the inverse operation. So whenever you see an addition sign, we're going to use the opposite of that, the inverse of that, to solve for the variable or isolate the variable. In this case, we have my equation, and as I separate it here, I have 4 and m, they're squished together. Remember that when they're squished together like that, there's a multiplication sign in between the number with the variable. And so for multiplied by m, the inverse of there's a multiplication operation there. The inverse of multiplication is division. Now, when you think division, sometimes we think like this: divide by 4, divide by 4. But when solving equations, we don't really use this symbol very much. We use the fraction bar symbol. So what I'm going to do is I'm going to write it like a fraction bar, but I am still using the inverse of multiplication, which is division. So I'm going to divide both sides by 4. Again, you can think of it as dividing by 4, but really we're dividing by 4. And a lot of times that number over here on the right-hand side might not work out evenly, so the fraction, the improper fraction, is actually the solution. So that's another benefit to using the fraction. Anyway, 4 divided by 4 is 1, and 1 times m is still m. That's again the identity property of multiplication. On the right-hand side of the equation, I have 20 over 4 as a fraction, or 20 divided by 4 as a division problem, however you would like to think about it. And I know that 20 divided by 4 is 5. So m must equal 5 in this case. All right, so we're just doing one operation, and it's the inverse operation of whatever's next to the variable. Again, let's take a look at another problem. It's a one-stepper. I have 3 multiplied by x, and so the inverse of multiplication is division. I will divide both sides by 3. I know that 3, or think of it this way if you would like, but I would like you to write it like a fraction bar. Okay, 3 divided by 3 is 1, or 1 times x. And 15 divided by 3 is 5. Well, I know that 1 times x is still just x with the identity property multiplication, so x must equal 5. All right, so we're using that one operation to solve that equation. And so in the past, we would have had 3 variables here equal to 15. And we would have had to figure out how much each one was worth, and we've done that actually with the scale, but now we're going to do it algebraically. And so we have a few more division problems, or multiplication problems that we will use the inverse of division to solve. In this case, we have 2 times x, and we're trying to get this x all alone. So we're going to divide both sides by 2. I know that x, or 1x if you would like to think of it that way, is equal to 20 over 2, or 20 divided by 2. It's the same thing, in this case 10, but we know 1 times x is 10, so x must equal 10. A rule of thumb is that we don't ever write the 1 in front of the x. It's just understood to be there. It's understood as 1x. So please don't write the 1x on your answers. Make sure it just is x equals 10. And then finally, we're going to actually skip out this step because I think that you understand, or I hope that you understand that 2 divided by 2 is 1, and 1x is still x. So in this case, I still have multiplication. The inverse is division, so I know that x must equal 9. And again, a lot of these problems you could do with mental math, but we're going to practice an algebraic process so that when the problems become more difficult, you will know how to keep your work organized. Finally, and this has to do with what we just talked about, we have some division problems here. And so let's separate our equation into 2 parts. The left side and the right side each has an expression, and use inverse operations to solve for k. So the goal is to get this variable all alone on the left-hand side. In this case, it is being divided by 8. And either the inverse of division is multiplication. So I'm going to multiply each side by 8, like so. And so sometimes you might have learned that, your teacher may have written it like this. And I'm guilty of doing the same thing with addition and subtraction because it's easier for me to visualize the addition and subtraction that way. But it's not easy to visualize multiplication by writing it underneath. So I'd like you to write it next to, because when I visualize multiplication, I always think, Mr. Gillum as a math teacher always thinks, oh, this is multiplying fractions. I can reduce, reduce, cross reduce, cross reduce. So in this case, I know 8 goes into both 8 and 8. And so all I'm left with is 1k over 1 is equal to 16. Well, I know that 1 times k is still k, and k divided by 1 is still k. So in this case, k equals 16. Again, I'm a little guilty of writing our addition and subtraction underneath because I think it's easy to visualize like this when I see my addition up and down. Well, with multiplication, I like to see it from side to side. So again, I have this problem and I see that I want x by itself. The inverse of division, which is that fraction bar, is multiplication. So I'm going to multiply each side by 3, or 3 over 1, however you'd prefer to think of it. I see that I can cross-reduce the 3's, and I'm left with just 1x over 1, or x equals 12. So today's lesson, what I want you to be able to do is use one inverse step, to get the variable isolated on one side of the equation. All right, we'll practice some more of this in class. That's all for today.